Welcome back, Design Junkies, to Mechanical Engineering Made Simple. If the podcast brings you value, help support the show with a like, a follow, or leave a comment below.
Honestly, it's just great to be back in the studio. I love diving into this stuff.
Yeah, I'm super excited for this one. So to start us off, I want you to picture this. It's September 1999.
Oh boy, I know exactly where this is going.
Right. So NASA scientists are all gathered in a control room, and they're watching the telemetry from the Mars Climate Orbiter.
Which was, what, a massive, incredibly expensive piece of hardware.
Yeah, like 125 million bucks, absolute engineering brilliance. And it's approaching the red planet after a 10-month journey. And then the signal just vanishes.
It doesn't just fade out, right? It literally disintegrates.
Exactly. It disintegrates in the Martian atmosphere.
Mm-hmm.
And the reason wasn't, a meteor strike or some faulty solar panel. It was a math problem.
A unit translation error.
Yeah. One engineering team used metric units for their thrust calculations, and another team used English units. And that one simple, tiny translation error sent this massive orbiter crashing right into the atmosphere.
I mean, it really is the ultimate nightmare scenario for any engineer, but it perfectly illustrates the stakes of what we're unpacking today.
It really does.
Because the physical world around us, like the skyscrapers that don't fall over or commercial airliners staying pressurized, even the water pumps that just run for 30 years straight without breaking, they are all held together by this hidden universal language.
Right, strict mathematical laws and material reality.
Exactly.
And for you, the listener, whether you're a seasoned engineer designing, high-pressure turbines, or you're just insanely curious about how machines don't tear themselves apart under millions of pounds of force, this deep dive is going to fundamentally change how you look at a piece of metal.
It really will, because we're going to explore those invisible rules.
Let's start with that language you just mentioned. Because before you can even begin to design a system, you need a vocabulary, right? Like a way to describe what the physics are actually doing.
Yeah, and you need a vocabulary that leaves absolutely zero room for misinterpretation. So in the realm of transport phenomena and thermodynamics, that language relies heavily on specific Greek symbols.
Which, if you're an outsider, it just looks like a bowl of alphabet soup.
Oh, totally. But it's actually a highly evolved shorthand.
Let's slow down and actually look at some of these letters, because I think people assume an engineer just writes the word temperature or heat on a whiteboard and calls it a day.
Not even close.
Right. It's so much more granular than that. Let's take the concept of a material expanding when it gets hot.
Okay, yeah, thermal expansion. So if you're designing a steel bridge, you know the summer heat is going to make that steel physically grow.
Because things expand when they heat up.
Right. But the question is, how is it growing? We use the symbol alpha to represent the linear thermal expansion coefficient.
So alpha is just one direction.
Exactly. It tells you how much a beam will lengthen in one single line. But if you're designing a solid block or, a complex three-dimensional component, linear expansion isn't enough. You need beta.
And beta is what? The volume?
Yeah, beta is the cubic thermal expansion coefficient. It maps how the total volume changes. And then taking it a step further, we have gamma, which represents the cubic mass expansion coefficient.
Wait, okay, I need to visualize this. If I have a solid cube of aluminum and I heat it up, alpha tells me how much taller it gets. Beta tells me how much more space the entire cube takes up. But what is gamma actually doing? Like, how does mass expansion differ from volume?
That's a great question. Gamma becomes critical when we start dealing with fluid dynamics. So systems where the actual density of the medium is shifting.
Oh, so it's not just a solid block anymore.
Right. It ties the expansion back to the mass of the material itself under varying states. And speaking of fluids, this is where the Greek letters get even more specialized.
Okay, lay it on me.
You have eta for dynamic viscosity, and you have nu for kinematic viscosity.
Okay, let me pause you right there, because viscosity is a word everyone uses. Like, we all know honey is more viscous than water.
Sure, yeah.
But why do engineers need two completely different symbols, eta and nu, for what seems like the exact same concept?
Because they measure two fundamentally different mechanical realities.
How so?
So dynamic viscosity, that's eta, is a measure of the fluid's internal friction. It's the raw physical force required to shear the fluid apart.
Like pushing through it.
Exactly. Think about shoving a wooden spoon through a jar of really cold honey. The actual resistance you feel pushing back against your hand, that is dynamic viscosity.
Okay, that makes sense. So what is kinematic viscosity then?
Kinematic viscosity is dynamic viscosity divided by the fluid's density. It basically describes how the fluid flows under the force of its own weight. usually, due to gravity.
Oh, so it's about how it moves on its own, not how hard it is to push.
Right. Exactly. If you take that same jar of honey and pour it out onto the counter, how fast it spreads is dictated by kinematic viscosity.
That distinction is incredible. So if I'm designing a pump, I need Ada to know how powerful my motor has to be to push the stuff.
Yes, and if you're designing the pipes that the fluid flows down, you need none to know how it's actually going to travel.
You're designing for the motor's effort versus the fluid's behavior.
You nailed it. And to track that actual movement, we use flow rate symbols. We use the letter phi as our baseline. So phi sub v denotes volumetric flow rate. That's how much raw space the fluid takes up as it passes a specific point.
Got it.
Then you have phi sub dam, which is mass flow rate. That tells you how many actual molecules are moving past that point.
Which is different from volume because of density.
Exactly. Then we use phi sub q for heat flow rate mapping the transfer of thermal energy, and phi sub w for the flow of work or power.
It's just a beautifully precise language. I mean, if an engineer in Tokyo writes an equation using phi sub q, an engineer in London knows instantly they are calculating heat flow, not volume.
It's universal.
But here is where my admiration for this whole system just hits a brick wall. Because that beautiful, universal language slams headfirst into the absolute nightmare that is the U.S. inconsistent system of units.
Oh, man. Don't even get me started.
I mean, seriously, why hasn't the engineering world just burned the imperial system to the ground?
Believe me, I know plenty of engineers who would love to do exactly that. But it really just comes down to the sheer inertia of legacy infrastructure.
Like old blueprints and machines.
Decades of them. We have over a century of heavy machinery, manufacturing plants, aviation blueprints, and foundational reference tables built entirely on the U.S. customary system.
You can't just hit a massive translate button.
No, you can't. We cannot simply flip a switch to metric without fundamentally redesigning the entire industrial foundation of the country. So we're stuck dealing with the infamous difference between pound mass, which is denoted as pound, and pound force, denoted as pound F.
And this is where things get genuinely dangerous, right?
Yeah.
Especially in fluid statics. Because fluid statics deals with fluids at rest, or moving at a constant velocity without acceleration, like water sitting in a municipal water tower.
Exactly. And in these baseline pressure calculations, confusing mass with weight or density with specific weight, it will completely corrupt your math.
Because they aren't the same thing.
Right. Pound mass is a measure of the actual physical matter in an object. Pound force is a measure of the gravitational pull acting on that matter.
So on Earth, at sea level, 1 pound mass happens to exert 1 pound force.
Yes.
Which means they're numerically similar. And I imagine that creates a massive false sense of security for someone just plugging numbers into a calculator.
It creates a catastrophic false sense of security. In the physics equations that govern fluid statics, mass and force are entirely different variables behaving in completely different ways.
Right.
If you plug a pound mass value into an equation that is expecting a force, your units will not cancel out. The math literally breaks.
It's like telling a builder to cut a board 3 lengths long without specifying if you mean inches or centimeters.
Exactly. It's meaningless and dangerous.
So what's the golden rule here? If I'm an engineer looking at a legacy blueprint and a fluid's mass is listed in poundsum, what do I actually do to make sure the water tower I'm designing doesn't burst and flood the town?
There's a very rigid rule of thumb. If mass is ever given in poundsum, which belongs to the inconsistent system, it absolutely must be converted to slugs before you can use it in a consistent equation.
Slugs. I'm sorry, it just sounds so primitive for a modern science. How heavy is it? Oh, about 50 slugs.
It does sound ridiculous, but mathematically, the slug is the base unit of mass in the consistent U.S. system. To get there, you take your pound value and divide it by 32.174.
And that number? 32.174. That is the standard acceleration of gravity on Earth, measured in feet per second squared.
You've got it. If you forget that single step, if you forget to divide by 32.174 and you plug pound mm directly into an equation requiring slugs, your resulting pressure or force calculation will be off by a massive factor of 32.
Oh, wow. That's not a rounding error.
No, that is the difference between a submarine hull holding strong or imploding instantly.
It's exhausting just thinking about the mental overhead required to carry that unit translation burden all the time.
Yeah.
You're constantly acting as this mathematical diplomat between two warring nations.
That's a perfect way to put it.
I mean, you have to convert joules of energy into British thermal units, or realize that 1 kilowatt-hour of electricity translates to over 2.6 million foot-pounds of work.
And the translation is vital because the math is only going to get more complex from here. I mean, fluid statics is challenging because fluids are, well, fluid. But when we transition to solid objects under heavy loads, we're talking steel beams, aluminum struts, titanium engine mounts, we enter the math of deformation.
Because nothing is actually perfectly solid.
Exactly. At a microscopic level, nothing is truly solid. Everything bends.
Right, and figuring out exactly how a solid piece of metal will bend, or stretch, or break, that relies on the concepts of stress and strain.
And we use very strict conventions to map this out. In engineering mechanics, tension, which is the act of pulling something apart, is always considered positive.
Okay, pulling is positive.
And compression, pushing something together, is considered negative.
That makes intuitive sense. You pull on a steel rod, you're adding length, so it's a positive change. You compress it, you reduce length, so it's a negative change.
Exactly.
But the actual mathematical relationship between the stress you apply, the force, and the strain, the material experiences, the deformation, it's intensely complex. We aren't just using a simple fraction here, right? We are dealing with tensor matrices.
We have to. To calculate how a solid object deforms, engineers use what is known as the stiffness matrix. It's usually represented by a stylized E.
Okay, the E matrix.
Right. And the mathematical relationship states that the stress vector, which contains components spanning from sigma 1,1 down to sigma 3,1, is equal to the stiffness matrix E multiplied by the strain vector.
And the strain vector has its own components.
Yeah, it contains components from epsilon 1,1 all the way down to 2 times epsilon 3,1.
Okay, let me just jump in here because my brain is starting to smoke a little bit.
It's heavy math, I know.
Why can't we just use a simple ratio? Like if I have a piece of taffy and I pull on it with 5 pounds of force, it stretches 1 inch. If I pull with 10 pounds of force, it stretches 2 inches. Why do we need a massive matrix full of sigma and epsilon coefficients just to figure out if a structural beam will flex?
Because you aren't pulling on a one-dimensional line in a vacuum. We live in a three-dimensional world. When you apply force to a material, it never reacts in just one perfect direction. You're dealing with normal stresses, which are forces directly pulling the atomic lattice apart or pushing it together.
Right.
But you are simultaneously dealing with shear stresses, which are forces causing layers of the material to slide laterally across each other. And this chaotic microscopic ballet is happening simultaneously in the X, Y, and Z axes.
Okay. Let's see if I can visualize this. Imagine I have a solid square block of rubber sitting on a desk.
Good example.
If I take my hand and push straight down on the top of it, I am putting it into compression, which is a negative stress in the vertical z-axis.
Right.
But the rubber doesn't just disappear. As it gets shorter, the material has to go somewhere, so it visibly bulges out the side.
Exactly. The vertical compression physically forces the material to expand laterally into the X and Y axis. So a negative compressive stress in one direction is instantly generating positive tensile strains in 2 completely other directions.
Oh, wow. So every single action has this chaotic multi-directional reaction.
And that lateral bulge is the exact reason the stiffness matrix E must be a 6x6 grid. It maps to the 6 independent components of stress and strain in 3D space.
That is wild.
This matrix contains 36 individual coefficients, ranging from E1111 all the way down to E1313. The matrix is basically a hyper-detailed mathematical map. It predicts how every single push, pull, or twist in any one direction will cause a corresponding bulge, shrink, or shear in every other possible direction.
And from what I understand, this E matrix is perfectly symmetric.
Right.
Like, if you draw a diagonal line down the center of the grid, the coefficients on the top right mirror the coefficients on the bottom left. Why is that?
That symmetry is actually one of the most beautiful aspects of solid mechanics. Because there is a scalar energy function at play, the matrix has to be symmetric. It perfectly reflects the fundamental physical law of the conservation of energy within a material's elastic limits.
Conservation of energy.
Yeah. The mechanical work you do to deform that block of rubber is stored inside the molecular bonds as elastic potential energy.
Like a coiled spring.
Exactly. The specific path you take to squish the block doesn't matter. The total energy stored is mathematically conserved. So the symmetry of the matrix perfectly mirrors the physical reality of the universe.
Man, that's almost poetic. But this is where the conversation has to pivot from theory to reality, doesn't it?
Oh, yeah.
Because you can have the most elegant, perfectly symmetrical, 36 coefficient stiffness matrix in human history. You can calculate your sigmas and epsilons down to the 5th decimal place. But if you walk onto the factory floor and build that part out of the wrong chunk of metal, the machine will just tear itself apart.
Absolutely. The math is merely a mat. The metal is the territory. We often fall into this trap of using generic terms, right? Like steel, aluminum, copper.
Just make it out of copper.
Exactly. But in the world of mechanical design, handing an engineer a block and saying it's copper is almost entirely unhelpful.
It's what we call the metal menagerie.
Yeah.
You're never really dealing with pure elemental copper right off the periodic table.
Almost never.
You're looking at a vast, highly specific ecosystem of alloys where the base copper is tailored with incredibly precise fractional percentages of trace elements.
We're talking about adding highly controlled pinches of tin, lead, zinc, iron, or nickel, and these microscopic additions completely rewrite the physical destiny of that metal. Let's look at two specific real-world examples.
Let's do it.
Take the copper alloy, designated as C93700.
Okay, C93700. What is the actual chemical makeup of that?
It's heavily alloyed with tin and lead, and this specific metallurgical recipe is engineered to create high-speed, heavy-pressure bearings.
Oh, so it takes a beating.
Huge beatings. It is predominantly used for massive slide guides and steel mills, and for applications that require intense acid resistance, like pumps handling corrosive sulfite fluids.
But why lead and tin? What do those trace elements physically do to the copper?
Well, the lead acts almost like a solid microscopic lubricant suspended within the copper matrix.
Wait, really? Solid lubricant?
Yeah. When you have two massive steel components sliding against this bearing under tons of pressure, the lead literally smears at a microscopic level. It prevents the bearing from seizing up or welding itself to the steel from the friction.
That is fascinating.
And the tin provides the underlying structural rigidity, so the whole thing doesn't just collapse.
So C93700 is this gritty, heavy-duty, chemically resilient workhorse.
Exactly.
But then you have a completely different recipe, like alloy C95800.
Completely different animal. If you tried to use C95800 as a slide guide in a steel mill, it would fail miserably.
Why?
Because C95800 incorporates elements like aluminum and nickel. This completely changes the crystal structure. It is tailored specifically for propeller blades, propeller hubs, and high-stress marine equipment.
Because the nickel and aluminum create a tight, highly protective oxide layer on the surface of the metal that violently resists saltwater corrosion.
You got it.
So here's where it gets really interesting. While the steel mill bearing needs lubricity to survive friction, the marine propeller needs raw tensile strength to survive the twisting torque of the ocean without rusting away. It really is like baking, isn't it?
It's exactly like baking.
A pinch of yeast gives you a fluffy loaf of bread. A pinch of baking soda gives you a dense biscuit. The base ingredient is still flour, but the destiny is entirely altered.
And the baking analogy goes even deeper, because it's not just about the ingredients you mix into the bowl. It's about how you apply the heat.
Ah, the manufacturing side.
Right. In metallurgy, the manufacturing method, specifically the casting method, is just as critical as the chemical recipe. The established reference standards will literally specify entirely different strength properties for the exact same alloy, depending on whether it was sand cast, permanent mold cast, or centrifugal cast.
Let me stop you there, because that sounds counterintuitive. If I have a vat of molten C95800 propeller alloy, why does the physical strength of the final part change, depending on what kind of bucket I pour it into? The chemistry hasn't changed.
The chemistry hasn't changed, but the microscopic architecture of the solid metal has. It all comes down to the cooling rate and how the crystal grains nucleate and grow.
Okay, walk me through that.
Let's take sand casting first. You pack special foundry sand around a wooden pattern, remove the wood, and pour your 2,000-degree molten metal right into the hollow cavity in the sand. Now, sand is an incredibly good thermal insulator.
Right, think of being at the beach. The top layer of sand is hot from the sun, but if you dig an inch down, it's cool. It just traps the heat.
Precisely. Because the sand traps the heat, the molten metal inside the mold cools down very, very slowly. This slow cooling gives the metallic crystals a long time to grow large and coarse.
And large crystals mean what for the metal?
Large grain structures generally mean a softer, more ductile metal with lower overall tensile strength.
So it's a bit squishy, relatively speaking.
Right. Now contrast that with permanent mold casting.
Okay, how does that work?
In permanent mold casting, you pour that exact same molten metal into a reusable mold made out of heavy steel or iron, and metal is a fantastic thermal conductor.
So it pulls the heat out.
Violently. The instant the liquid copper touches the iron mold, the mold sucks the heat out of the liquid. The copper chills and solidifies incredibly fast. Because it cools so quickly, the crystals don't have time to grow large at all.
So you get tiny crystals.
You get a very fine, tight, densely packed grain structure. A tighter grain structure fundamentally traps microscopic defects, making the resulting part significantly stronger and harder than the sandcast version.
Same chemistry, totally different strength.
Exactly.
And then there's centrifugal casting, which just sounds like something out of a sci-fi movie.
It's one of my favorites. It's a brilliant mechanical solution to a chemical problem. You basically pour the liquid metal into a cylindrical mold that is spinning at incredibly high speeds.
Like a centrifuge.
Exactly. The centrifugal force throws the dense, heavy, pure liquid metal aggressively against the outer walls of the mold. Meanwhile, any trapped gases, oxides, or lighter slag impurities are physically forced to float to the inner diameter of the cylinder.
So you are basically spinning the trash right out of the metal.
That's exactly what you're doing. Once it cools, you take this massive metal tube out and you use a lathe to physically machine away the inner layer of trash.
Oh.
What you're left with is a cylinder of exceptionally pure, highly dense, flawless alloy.
Wow. So you really cannot separate the math from the material, and you can't separate the material from the manufacturing.
Right.
You simply can't just pick a metal out of a catalog based on a single number.
You'd be setting yourself up for failure if you did.
But as complex as marine engineering and steel mills are, things take a massive leap in difficulty when we introduce extreme environments. I mean, designing a copper bearing for room temperature is one thing. Designing for an aerospace vehicle that transitions from freezing altitudes to burning atmospheric re-entry is entirely different.
The heat of the moment. Yeah, when we shift our focus to aerospace, we leave the copper behind entirely. We start looking heavily at highly specialized materials like stainless steels.
Like the 301 and 17.7 pH grades.
Exactly. And high-strength aluminum like the 7C75 series. And the fundamental enemy of every single one of these metals is temperature degradation.
Right. We talked earlier about the stiffness matrix, the modulus of elasticity, denoted as E. We also have these critical strength parameters defined by the baseline physics, right?
Right.
F sub 2, which is the ultimate tensile strength,
Mm-hmm.
F sub T, the tensile yield strength,
Yeah.
and F sub C, the compressive yield strength. So at room temperature, a piece of 7-75 aluminum is incredibly strong.
Yeah.
But as the temperature rises, what is physically happening inside the metal?
The atomic bonds are vibrating. Remember, temperature is simply a measurement of atomic kinetic energy. At room temperature, the atoms in the aluminum lattice are relatively calm. They're locked in place. But as you introduce a heat source, say the skin friction of a jet flying at Mach 2, those atoms absorb that energy and begin to vibrate violently. As they vibrate, they push against each other, physically increasing the distance between the atoms.
The material expands, which we
Mhm.
talked about with the alpha coefficient earlier.
Yes.
But more importantly, it softens, right? The atomic bonds are stretched, so the metal loses its stiffness, its E value, and its ultimate yield strengths. The F sub 2 and F sub E just plummet.
They fall off a cliff.
But the most terrifying aspect of aerospace design isn't just figuring out how hot the wing gets. It's figuring out how long it stays hot.
Time is the hidden dimension of engineering failure. When you examine the advanced material data for aerospace alloys, the curves don't just plot strength against temperature. They plot it across vastly different timescales.
How
You'll see one curve demonstrating the metal strength after a half-hour exposure to heat, but right next to it, there are completely different, much lower curves plotting a 1,000-hour or a 10,000-hour exposure at temperatures ranging from room temperature all the way up to 1,000 degrees Fahrenheit.
Okay, let me make sure I understand the physical implication of this. Why does a piece of stainless steel care if it's been at 600 degrees for 30 minutes versus a month? I mean, it's the exact same temperature.
It cares because of a phenomenon called creep.
Creep.
Yeah, and it leads to total metallurgical instability. Imagine an interceptor aircraft executing a supersonic dash to catch a target. The leading edge of the wing heats up to 600 degrees due to friction, but the dash only lasts 30 minutes.
Okay, so a quick sprint.
Right. The thermal energy stresses the atomic lattice, and the ultimate strength of the metal temporarily drops, but the core crystal structure holds its shape. When the plane slows down and cools off, the atoms settle back into their original positions.
But if I take that exact same aluminum wing and I somehow run it at 600 degrees continuously for 1,000 hours, what then?
The material fundamentally relaxes. Even if the aerodynamic load on the wing remains exactly the same, that continuous, unrelenting thermal energy allows the atoms to slowly, permanently slide past one another.
Oh, wow. So it literally loses its shape.
Microscopic dislocations within the crystal lattice begin to migrate and pile up. The material slowly stretches out of shape. That is creep. After 1,000 hours at 600 degrees, the metal's internal architecture is so distorted that its ultimate strength drops by a massive percentage compared to its half-hour rating. It becomes metallurgically unstable.
And engineers use mathematical models called Ramberg-Osgood curves to plot this behavior out, right?
They do.
And it is wild to look at how these curves behave. As the temperature gets higher, the stress-strain curve flattens out incredibly aggressively.
The Ramberg-Osgood equation is vital because it maps the nonlinear relationship between stress and strain right at the tipping point where a material yields.
Okay.
When a metal is cold, it behaves elastically. It acts like a very stiff spring. You pull it, and if you let go, it snaps perfectly back to its original shape. The stress-strain curve on a graph is a steep upward diagonal line.
But as it gets hot and creep sets in, it yields much sooner. It stops acting like a stiff spring and starts acting more like, I don't know, warm taffy.
Yeah.
The curve flattens horizontally, which means even a tiny microscopic increase in force causes a massive amount of permanent plastic stretching.
This is exactly why aerospace material selection is so incredibly unforgiving. An internal engine component designed to run at a steady 400 degrees for a 10-year commercial lifespan requires an entirely different alloy than a re-entry capsule plunging through the atmosphere.
Right, because the capsule is taking a brutal, searing 1,000-degree blast of plasma, but it only lasts for exactly 15 minutes before splashing into the ocean.
Right. It doesn't need to survive 10,000 hours. It just needs to not melt for 15 minutes. The math dictates that you absolutely must design according to the time at temperature charts.
And yet, heat isn't the only thing that degrades a material over time. Even if you keep a machine perfectly cool in a climate-controlled room, the metal will eventually just get tired.
Wear, tear, and fatigue. This introduces the realm of fatigue and crack initiation analysis because in the real world, things rarely just explode or snap on day one.
They fail on day 1,000, seemingly out of nowhere.
Exactly.
Let's explore that mechanism. If I buy a brand new, massive steel crane rated to lift 10 tons, and I try to lift a 50-ton concrete block with it, the steel booms will groan and snap immediately. That's a massive, catastrophic overload. It exceeded the F sub 2, the ultimate tensile strength.
Sure.
But that isn't how most machines fail, is it?
Not at all. In aerospace, automotive, heavy industrial applications, catastrophic overload is actually quite rare. Most failures occur under normal, everyday operating loads that are mathematically well within the material's theoretical limits.
So why do they break?
They fail because of millions of tiny, invisible microscopic cycles.
Let's use a visual analogy for the listener. If I take a metal paperclip and I bend it just a tiny bit, maybe 10 degrees, it springs right back. I haven't exceeded its yield strength.
Right.
But if I sit at my desk and bend that paperclip back and forth, up and down, 50 times, the metal right at the bend gets hot, it feels soft, and suddenly it just snaps with almost zero force.
That paperclip is the perfect representation of fatigue mechanics. Every single time you bend it, even slightly, you are initiating microscopic slip bands within the crystal structure of the steel. You are forcing the atoms to shuffle back and forth.
And that adds up over time.
Over thousands of cycles, those slip bands accumulate and coalesce into microcracks right at the surface.
And once a crack starts, it's pretty much game over, right?
Oh, absolutely. The crack fundamentally changes the geometry of the part. The force you're applying can no longer distribute evenly through the metal. It concentrates entirely at the microscopic tip of the crack.
Like a wedge.
Exactly. It rips it deeper and deeper with every subsequent cycle until the remaining solid metal is just too thin to hold the load, and it snaps. But there are culprits that accelerate this process long before it should naturally occur. The two biggest enemies are residual stresses and notches.
Okay, let's talk about notches, because I think people assume a notch means someone took an axe and hacked a chunk out of a beam. But in engineering, a notch is far more subtle, isn't it?
Much more subtle.
Like if I have that same paperclip, and before I start bending it, I take a razor blade and put a tiny, barely visible scratch in the metal. It'll take half the amount of bends to break it.
Probably far less than half. In fatigue analysis, a notch is any geometric discontinuity. It is any feature that interrupts the smooth flow of force through the part.
So not just a scratch.
Right. It could be an accidental scratch from a mishandled tool, sure, but more often, it's a design feature. It could be a poorly calculated fillet radius where a spinning shaft steps up to a wider diameter. It could be a sharp inside corner on an L bracket. Or if we're talking powder metallurgy manufacturing, it could be a tiny feather edge of flash left over from the pressing die.
And engineers refer to these geometric interruptions as stress risers. How does a stress riser actually work on a physical level?
Imagine the force traveling through a solid metal beam like water flowing smoothly down a river. If you suddenly narrow that river with a sharp concrete wall, a notch, the water can't just flow through the wall.
It has to violently speed up and flow around the sharp corner.
The exact same thing happens to mechanical stress. The lines of force cannot flow through empty space. They have to bunch up and crowd around the root of the notch.
So the overall load on the machine might be low, but the localized stress exactly at the tip of that microscopic scratch might be 3, 4, or 5 times higher than anywhere else in the part. It acts like a magnifying glass for the force, aiming it directly at the spot where a microcrack desperately wants to form.
You've got it. And when you combine a geometric notch with residual stress, you have a perfect recipe for sudden, catastrophic failure.
What exactly is a residual stress? It sounds like the part is stressed out before it even goes to work.
It literally is. Residual stresses are internal, locked-in forces that exist in the material before you even apply an external load. They're usually the invisible scars of the manufacturing process.
Give me an example.
For example, if you weld two heavy steel plates together, the molten weld pool is incredibly hot and expanded. As it cools down to room temperature, it wants to shrink. But because it's fused to the cold steel around it, it can't shrink completely.
So the weld is permanently locked in a state of tension, trying to pull itself apart just sitting on the shelf.
Precisely. If the surface of a part has a massive tensile residual stress locked into it, and you introduce a geometric notch, and then you put that part into an engine where it undergoes a million cycles of vibration, the part is doomed. The fatigue crack will initiate almost immediately.
And predicting exactly when that crack will initiate is notoriously frustrating for engineers, isn't it? You have to account for real-world loadings, which are never as clean as laboratory tests. You have to use temperature interpolation to adjust your math if the machine runs hot. But the most maddening variable is material scatter.
Oh, material scatter. It is a deeply humbling concept for any engineer who loves precise, deterministic math.
Why is that?
Scatter is the inherent unavoidable statistical variability within the physical material itself. You can take a billet of aerospace alloy, forge two supposedly identical brackets, machine them on the exact same robotic CNC mill, and put them in the exact same testing rig under the exact same cyclic load.
And they don't break at the same time.
Never. One bracket might fail at 150,000 cycles. The identical twin bracket might survive to 600,000 cycles.
Wait, how is that physically possible if everything is identical?
Because at the microscopic atomic level, nothing is truly identical. The distribution of microscopic impurities, the exact alignment of the crystal grain boundaries, the presence of a microscopic void that occurred during casting, it is completely chaotic. You cannot perfectly predict the path a fatigue crack will take.
You're no longer dealing with absolute mathematical certainties. You're relying on statistical probabilities.
Exactly.
Which means you can't just build a machine, turn it on, and walk away trusting the math. If you can't perfectly predict when a fatigue crack will initiate and propagate to failure, you have to constantly monitor the health of the machine while it's running. You have to catch it in the act of failing.
Good vibrations and bad ones. This brings us to the vital discipline of vibration monitoring. It is essentially the electrocardiogram for heavy machinery.
I love that analogy.
How do we know a massive high-pressure turbine is developing a microscopic fatigue crack in its internal shaft? We listen to how the machine shakes.
But you can't just slap a sensor anywhere on the machine indiscriminately. I was fascinated to learn about the rigorous global standards dictating exactly how and where you are legally allowed to measure these vibrations. The two titans here are ISO 7919 and ISO 100816.
And they govern two completely different philosophies of measurement. ISO 7999 covers measurements taken directly on the rotating shafts of the machine.
So measuring the moving part itself.
Right. While ISO 9816 covers measurements taken on the non-rotating structural parts, like the massive outer casing or the bearing pedestals bolted to the floor.
And choosing between those two standards isn't just a matter of preference or budget. An engineer can't just say, well, it's easier to magnetically attach a sensor to the outside of the casing, so let's just do that.
Absolutely not. And this is where one of the most critical documents in vibration analysis comes into play. The Hiroshi Kanki umbrella document.
Hiroshi Kanki.
Yes. It provides a strict, mathematically driven decision tree to determine exactly where you must place your sensors to get a truthful reading of the machine's internal health. You have to calculate two variables, shaft displacement and the dynamic stiffness ratio.
Okay, let's break the math down. Shaft displacement is defined by the formula. X sub F equals the sign of the quantity lowercase l divided by 2 times uppercase L. This is essentially looking at the physical geometry of the shaft and how far it physically deflects from a perfectly straight center line when it spins.
Correct.
But the variable that really controls the decision tree is the stiffness ratio, denoted by the Greek letter alpha.
Alpha is the key to everything here. Mathematically, alpha equals z sub 2 divided by z sub 1.
Okay, what are the z's?
In mechanical terms, z sub 2 represents the dynamic stiffness of the pedestal and the foundation the machine is bolted to. Z sub 1 represents the dynamic stiffness of the bearing holding the spinning shaft. So alpha is pedestal stiffness divided by bearing stiffness.
Okay, let's walk through the physical implications of this ratio. What happens if alpha calculates out to be less than 1?
If alpha is less than 1, it means the denominator, the bearing, is significantly stiffer than the pedestal supporting it. Imagine a vertical water pump using heavy-duty, tightly packed rolling element bearings, and the whole assembly is bolted to a relatively soft, flexible steel deck. The bearing is essentially rigid.
Because it's rigid, any vibration originating from the heavy spinning shaft is transmitted perfectly through the bearing and directly into the flexible steel deck.
Exactly. The structure shakes violently. In this scenario, the Hiroshi-Kanki decision tree dictates that you must use pedestal vibration measurement, following the ISO 816 standard. Placing sensors on the outside casing or the foundation will give you a highly accurate, truthful picture of the internal shaft's vibration.
But what if alpha is greater than 1? What if the foundation is stiffer than the bearing?
Then the physics completely flip. And this is incredibly common in massive power generation machinery. Imagine a steam turbine utilizing fluid film bearing.
Fluid film bearing.
Yeah, in a fluid film bearing, the heavy steel shaft doesn't touch metal. It essentially hydroplanes on a highly pressurized cushion of oil, and that entire assembly is bolted down to a monumentally stiff, million-pound concrete pedestal.
So the pedestal is rock solid, but the bearing, the oil film, is squishy. It acts like a giant shock absorber.
You've hit on the core problem perfectly. The fluid film isolates the vibration. The internal steel shaft could be whipping itself to death, bending under a severe fatigue crack, throwing massive amounts of vibrational energy. But because that energy hits the soft oil film, it is absorbed and dissipated. It never reaches the stiff concrete pedestal.
Whoa. So if you bolt a sensor to the outside casing of that turbine, the sensor might read absolutely zero vibration. The machine feels perfectly smooth to the touch, while inside it is milliseconds away from detonating. The sensor is lying to you.
Precisely. This is why, if alpha is greater than 1, the standard absolutely forbids relying on casing measurements. You must use shaft relative vibration measurement, guided by ISO 79919. Engineers must install specialized proximity probes that literally penetrate the outer casing, look right through the oil film, and measure the microscopic physical displacement of the spinning shaft itself.
And what if the alpha ratio lands right in the middle, say between 1/5 and 5?
Then you are in a complex gray area. Both the shaft and the pedestal have comparable stiffness. They're both moving relative to each other and to space. In this zone, you must use shaft absolute vibration measurement.
Which means what?
It requires a combination of probes looking at the shaft A and D seismic sensors on the casing, mathematically combining the signals to find the true vibration vector.
The real-world examples make this so clear. A high-pressure turbine has an alpha ratio of 5. The casing isolates the shaft. You must measure the shaft directly. A vertical pump has an alpha of 1/10. The structure acts like a tuning fork. You measure the pedestal.
It's all about knowing your machine.
And once you have these accurate measurements, the ISO standards provide evaluation zones to tell you if the machine is healthy, right?
Yes. They look at the root mean square, or RMS, vibration velocity, measured in millimeters per second, and they categorize machines into classes based on size and foundation stiffness. Class I is for small machines up to 15 kilowatts. Class 4 is for massive prime movers over 75 kilowatts mounted on relatively soft, flexible foundations.
And they grade the health on a curve from Zone A to Zone D. Let's walk through what these actually mean on a factory floor. Zone A is the ideal, right? The machine is brand new, perfectly aligned, running smooth as silk.
Exactly. Zone B means the vibration has increased slightly, but it's acceptable for long-term continuous operation. It's aging, but it's fine.
But then you hit Zone C.
Zone C is a warning shot. The vibration, let's say it's measuring around 7.1 millimeters per second on a Class 3 machine, has reached a level where microscopic fatigue damage might be accumulating. You can keep running the machine to finish a production batch, but you need to actively schedule maintenance.
But then there is Zone D. What does a Zone D vibration actually sound and feel like if you were standing next to it?
It is terrifying. The ambient noise in the room changes to a deep, rhythmic thrumming. You can literally feel the concrete floor shaking through your boots. Your teeth might literally rattle in your head.
That's intense.
At Zone D, the vibration velocity is so severe that catastrophic fatigue damage is actively occurring with every single rotation. The slip bands are tearing into massive cracks. You do not schedule maintenance. You hit the emergency stop button immediately.
It is so crucial to understand this context. These ISO structural resonance codes are looking at the long-term, years-long in-situ health of the machine. This is fundamentally different from other standards, like the API American Petroleum Institute standards used during initial shop testing.
Right. API standards are incredibly rigid acceptance criteria. If you buy a massive screw compressor for an oil refinery, the API standard might demand you measure the vibration in mil peak to peak, or inches per second peak, while the machine is still on the factory test stand. If it fails API, it never even gets shipped to the customer. ISO is how you keep it alive once it's actually installed.
This brings us to a massive conceptual pivot. We've gone from the microscopic grain structure of copper alloys to the time at temperature creep of aerospace aluminum, all the way up to the shaking foundations of a power turbine.
We've covered a lot of ground.
But none of this physics happens in a vacuum. A mechanical engineer isn't a mad scientist working alone in a dark room. They are part of a massive organization balancing budgets, schedules, and human lives. It's time to look at systems engineering and the bottom line.
Because if we connect all these microscopic dots to the bigger picture, an error at the molecular level, say, an engineer selecting a C95800 copper alloy that is susceptible to notch fatigue for a specific geometry will propagate entirely up the chain. It will vibrate into a Zone D failure and destroy a billion-dollar project.
And to prevent this, organizations like NASA employ incredibly rigid systems engineering frameworks. It is a gauntlet of reviews stretching from pre-phase A all the way through phase F.
Let's walk through that milestone alphabet soup because it is the structural framework of how modern engineering actually gets done in the real world.
It starts with MCR, right? The Mission Concept Review. This is basically a bunch of smart people in a room looking at a napkin sketch and asking, does this idea violate the laws of physics?
Pretty much. It is establishing the baseline feasibility. If it passes MCR, you move into phase A and eventually hit the SRR, the System Requirements Review. This is a brutal phase.
Why is it brutal?
This is where you establish exactly what the machine must do. You aren't arguing about whether to use aluminum or titanium yet. You are defining the exact thermal loads, the G-forces, and the expected fatigue life the machine will endure.
Then you move to PDR, the Preliminary Design Review. This is where the engineers bring their initial math to the table. They say, we think we can survive those thermal loads using this stiffness matrix and these Ramberg-Osgood curves.
And if the math holds up, you move to the most stressful room in an engineer's career, the CDR, the Critical Design Review.
The CDR.
At CDR, the design is essentially locked. You are presenting your final blueprints. You have chosen your exact copper alloys. You have calculated your dynamic stiffness ratios to place your vibration sensors. Once you pass CDR, the organization commits to spending millions of dollars to physically cut metal.
Which leads to the SIRR, the System Integration Review, where you take all these disparate pieces built by different teams and bolt them together. And finally, the ultimate test before launch, the ORR, the Operational Readiness Review.
The reason NASA demands documents like a system description to be drafted way back in Phase A and continually updated and finalized by Phase F is traceability.
Traceability. Give me an example of how that saves you.
Imagine an engineer working on a high-pressure pump in Phase B miscalculates the dynamic stiffness ratio, alpha. They think the foundation is stiff, so they specify casing vibration sensors.
But the oil film is actually absorbing the vibration.
Exactly. The pump is built, it passes its initial spin tests, and gets integrated into the spacecraft. But during the final full-duration test burns before the ORR, the internal shaft starts experiencing fatigue. Because the sensors are on the casing, they read Zone A perfect health. The system looks fine on paper.
But it's not.
No. The shaft violently shears in half, destroying the entire assembly. That single mathematical error in Phase B causes a massive catastrophic failure at the operational readiness review.
And a failure at ORR doesn't just cost a few weeks of schedule, it costs an astronomical amount of money. Which brings us full circle to engineering economics. You said something earlier that stuck with me. Engineering is the application of physics within the constraints of economics.
It's the absolute truth.
It absolutely does not matter if your design perfectly manages fatigue and thermal creep if manufacturing the part bankrupts the entire company.
You cannot separate the physical realities from the economic realities. And the most vital concept an engineer must understand is the time value of money, specifically governed by the present value equation.
Let's look at the math for that, because it's just as unforgiving as a stress tensor. The equation is present value equals the sum of cash flow C sub I divided by the quantity 1 plus the discount rate R raised to the power of I.
Right.
Let me translate this into plain English. What this equation is essentially proving is that money in your hand today is fundamentally worth more than that same exact amount given to you next year.
Exactly. Because of the opportunity cost of capital. If you have 1,000 units of currency today, you can invest it in a risk-free bond and earn a return. The discount rate, R, represents that expected rate of return. So future cash flows must be mathematically discounted to figure out what they're actually worth to you right now, today.
This creates a fascinating tension, doesn't it? If an engineer is terrified of a fatigue failure, they might say, let's over-engineer this shaft. Let's build it out of incredibly expensive aerospace titanium instead of steel, and let's install 10 custom proximity probes. Does that suddenly make the cash flow diagram go negative?
That is the daily war waged inside every engineering firm. Let's role-play a scenario. Imagine you are defending a project to the finance department. The project generates a future cash flow of 1,000 in year 1, 1,500 in year 2, 2,400 in year 3, and 1,600 in year 4.
Okay, so that's the money coming in later.
Right. If your company's discount rate is 10%, you have to discount those future returns using the present value equation.
So year 1's return of 1,000 is divided by 1.10 to the power of 1. Year 2's 1,500 is divided by 1.10 squared. Year 3 is divided by 1.10 cubed, and so on.
You sum all those discounted values together, and that final number is the absolute maximum amount of money the company should be willing to invest in your design today.
Yes, if the manufacturing cost of your over-engineered titanium alloys and your complex sensor arrays exceed that calculated present value, the project is economically dead on arrival. The physics might be flawless, but the company will reject it.
And time is the ultimate enemy here. The exponent is in the denominator of the equation. So if you have a delay, say, the pump fails a vibration test and you have to redesign the shaft, you push the project's launch back a full year.
Because you push those positive cash flows further into the future, the math exponentially destroys the present value of the project. A one-year delay can turn a highly profitable engineering design into a massive financial loss.
The math of money is just as strict as the math of a 6x6 material strain matrix. You use cash flow diagrams to map out investments, just like you use a stress strain curve to map out a material's yielding point.
It is all profoundly connected. I mean, the precise Greek symbols dictating fluid statics prevent the water tower from bursting. The microscopic trace elements in a bronze bearing prevent the steel mill from grinding to a halt. The thermal exposure curves dictate the survivability of a supersonic wing. The stiffness of a concrete pedestal dictates whether a vibration sensor is telling the truth.
And every single microscopic decision funnels upward into that present value equation. The physical laws of the universe ultimately dictate the economic realities of human progress.
Which leaves us with a fascinating and I think slightly provocative thought about the future of this entire discipline. We have spent this deep dive exploring the traditional hard-won empirical reference tables, the manual unit conversions, the physical testing, the established rules of thumb encoded in legacy documents like the ISO standards and the ML handbooks.
These rules were written in the blood, sweat, and bent metal of past failures.
But engineering is evolving rapidly.
Incredibly rapidly. Today, our computational power is almost unfathomable compared to the Apollo era. We can now run digital twin simulations that perfectly calculate those 36 coefficient strain matrices in real time. We can digitally simulate 10,000 hours of thermal creep on a microscopic atomic level before a part is ever sent to a foundry.
Which raises a terrifying question. As we rely more and more heavily on these flawless digital models, are we going to lose touch with the physical reality of the materials?
That is the danger. Will the traditional rules of thumb, the intuitive understanding of how a sand casting cools versus a permanent mold, become obsolete? Or worse, will our absolute, unquestioning trust in a digital simulation make us blind to the messy, chaotic, statistical realities of the physical world?
Right, because a computer simulation might calculate that a virtual titanium shaft has an infinite fatigue life.
But the computer doesn't know that on a Tuesday afternoon, a tired machinist accidentally left a microscopic scratch on the fillet radius.
The simulation doesn't know about the notch. It doesn't know about material scatter. A digital model is only as good as the physical assumptions fed into it. The math on the screen might look perfect, but the real world is always full of unpredictable heat, residual stresses, and hidden vibrations. Remember, design junkies master the critical few, or the trivial many will master you. If you're leaving this episode with something you didn't arrive with, drop a comment. Takes you a few seconds, but it tells me this workbench is worth keeping open.